Same disclaimer as usual. We're going to be talking about the cosmic microwave background radiation, its original discovery, and some of the subsequent experiments that have been done about it. All of this is done from my own memory, and so there may be some mistakes in the details of the information, but in general, the broader topics, or like the broader subject, is going to be treated fairly well, because this is what I study. So, well, I don't study the CMB, but I study astronomy, and here we go. So there's my appeal to authority. Anyways, back in the day, there were a number of papers that came out where scientists had predicted that if the universe started off based upon Hubble's law. So Hubble law basically is that Hubble had measured a bunch of galaxies and how they were retreating from each other. And then that sparked the idea that, well, if they're moving away from each other, then at some point in the past, or if you run the clock backwards, then they're moving towards each other, and eventually you get to a hot single location, some singularity where the universe was concentrated, and as a consequence of its concentration, it would have been very high temperatures. And so you just run through like the physics of what you would expect if you have an expanding gas of material, and you arrive at the point where you'd say, well, okay, so you have a hot expanding gas. That gas initially is high enough temperature to be ionized, and so it behaves like a bolt of lightning where it's opaque. But then as the universe continues to expand and cools off, then you go through the transition where the gas is no longer ionized, so it's not a plasma anymore, and it becomes neutral. And just like with a lightning bolt, when the air cools off, the air becomes transparent again. So when the lightning bolt strikes, you have very high temperatures. The gas it ionizes the atmosphere, and so the atmosphere becomes opaque, and so you see the bolt of lightning itself. But then as the air cools off, then the bolt of lightning then the air recombines, the electrons recombine with the atoms, and the atmosphere becomes transparent again, and so the bolt of lightning disappears. So the presence and absence of the bolt of lightning, when the lightning strikes, it's opaque because it's ionized the gas, and you have free electrons that basically block the light or interact with the light. And then when it becomes transparent, most of the light is able to pass through without any trouble. So the same thing would happen in the early universe. You have this expanding gas. As the gas expands and cools off, you go through this phase transition where it's initially opaque, and then it becomes transparent. And when it becomes transparent, all of the photons that were trapped are able to stream freely in all directions. And then you just run the clock forward and say, okay, time passes, and you would have this distribution of light that comes from a originally hot source. That light gets stretched out. It loses energy. For the energy density goes down as the fourth power of the size. So as the universe spreads out, there are a number of things that happen. So let me pull up a drawing pad so that I can demonstrate what's going on. So the energy density of the photons, let me make sure, let's pull it up so that we can see everything the way that we want it. Okay, the energy density of the photons drops as the temperature, or as the size. So the energy density drops as 1 over r to the fourth, where r is the typical size. Like you pick two fiducial points in the universe, and as they expand, they're going to move apart from each other. And then as that volume increases, the energy density of the photons goes down because you're spreading the photons out. So you have some number of photons, and then you spread the universe out, and now the same number of photons is occupying a larger volume, and so you have that effect. So if I were to break this up, it's 1 over the volume times another factor of the size. The reason for the other factor of the size is that the photons themselves, the energy of the photon is proportional to 1 over the wavelength of the photon. So shorter wavelength photons have higher energies, and longer wavelength photons have lower energies. Okay, so as the universe expands, you're taking photons with a wavelength like this, and you're expanding the wavelength like that. And so as the universe gets bigger, the photons get stretched out, and so the individual energies of all the photons also spread out with the size. So that's why the energy density of the universe in photons scales gets smaller with the fourth power of the size of the universe. Okay, so you run this forward in time, and then you say, if we were to look at all of these leftover photons today, what would you predict? And the answer is that you would predict an ambient photon background that has a temperature on the scale of like 3 Kelvin. Okay, so that was the prediction that was made. At the same time, another group that was not communicating, so these two groups were not communicating with each other, and this is a little bit off. Let me move this 1 second. Let me move this down just a little bit and pull this up there so you can see the 3 Kelvin at the bottom. Actually, what I need to do is adjust this thing a little bit. There we go. That's more like it. All right. So this was predicted by a group, and there was a group at Princeton that was building an antenna specifically to look for this 3 Kelvin background radiation that was from all directions. At the same time, and down the street from this group at Princeton, at Bell Labs. So Bell Labs is from AT&T. They did a bunch of science experiments, and there were these 2 radio people who were using this particular radio antenna to look up into space and see, what they could find. And they weren't looking up into space. They were testing the antenna to use it for other purposes, right? They weren't using it for astronomy. They were going to use it. They worked at AT&T. They were going to use it for telecommunications type research. And they had this Penzias and Wilson. They had this antenna, and they were pointing it in a direction, and they saw this background fuzz, this noise that they couldn't get rid of. And so they're like, well, maybe it changes. If we point it in a different direction, we'll be able to see this. So they moved it somewhere else, and the noise was still there. And they moved it somewhere else, and the noise was still there. So it didn't matter where they looked, but they still had this noise in the background. And then they thought, okay, maybe there's pigeons that are living in there. So they chase out the pigeons, they clean up the pigeon poo, and the background radiation, that noise was still in their receiver. So they were still seeing this noise. I believe they put some metallic tape across all of these things because maybe the noise is coming from reflections off of these internal surfaces. And no matter what they did, they couldn't get rid of this background noise. So they called the people at Princeton and said, hey, we've got this background noise in our instrument, and we can't seem to get rid of it. Any idea what it is? And the people at Princeton were basically like, well, you just scooped us because we were building something specifically to look for exactly what you found. They did ask, for example, what's the noise temperature that you're seeing? And the answer was, it's about 3 Kelvin. And so that was kind of the inadvertent, like the discovery of penicillin, it was kind of an inadvertent discovery of the cosmic microwave background radiation using this telescope. So they won the Nobel Prize for the investigation. The paper that went along with the discovery, if we pull up, not the images, but if we go to the paper itself, is actually pretty small. And I probably should have pulled this up, but I didn't. So let's see if they have, it doesn't look like, so I don't have this, maybe there's an archived version of this paper. That's an interview. All right. Anyways, if you find it, if you were to read this, the suggestion that this might actually be the cosmic microwave background radiation was like a small sentence at the very end of the paper. They describe everything that they did, and then it's like, and there's a potential that this could be, if you stretch your imagination a little bit, the leftover record of the cosmic microwave background from the Big Bang, basically. Although at the time it wasn't called the Big Bang. They published, all right, so what's going on here? So Jim Peebles, Robert Dickey, who was actually one of my advisors in graduate school, worked with Dickey on some other experiments. Dickey, Peebles, and Wilkinson. So the Brans-Dickey theory is an alternative formulation of gravity, like general relativity. Planning on majoring in physics, does it matter where university you get your degree in? Not necessarily, not for your undergraduate, but for your graduate program, it makes a bigger difference. Your last university is the one that matters the most in general. All right. At the same time, Dickey, Peebles, and Wilkinson at Princeton were preparing to search for the microwave radiation in this region of the spectrum. They reasoned that the Big Bang must have scattered not only the matter that condensed into galaxies, but also released tremendous blast of radiation. All right, so his friend a professor at MIT told Penzias about a preprint paper he had seen by Jim Peebles and the possibility of finding radiation left over from an explosion that filled the universe at the beginning of its existence. Penzias and Wilson began to realize the significance of what they believed was a new discovery. To avoid potential conflict, let's see. So they called, Penzias called Dickey at Princeton, who immediately sent him a copy of the still unpublished Peebles paper. Penzias read the paper and called Dickey again, invited him to Bell Labs to look at the horn antenna and listen to the background noise. Dickey, Peebles, and Wilkinson and Roll interpreted this radiation as a signature of the Big Bang. To avoid potential conflict, they decided to publish their results jointly. 2 notes were rushed to the Astrophysical Journal's letters. So Astrophysical Journal's letters are basically 5 pages long-ish. They tend to be short. Back in the day, they were even shorter. Today, you have a limit of 5 pages, where the regular Astrophysical Journal, you can have like 20 or 30 pages is pretty standard. Those are long. I hate reviewing papers that are that long. At first, Dickey and his associates outlined the importance of cosmic background radiation as substantiation of the Big Bang Theory. In a second note, jointly signed by Penzias and Wilson, entitled A Measurement of Excess Antenna Temperature at 4,080 megacycles per second. So those were the days. They reported the existence of a 3.5 Kelvin residual background noise remaining after they accounted for sky absorption component and 2.3 Kelvin instrument component. So there you go. They were awarded the Nobel Prize in Physics for their joint detection. They shared the prize with Peter Kapitsa, who won it for unrelated work. Peebles was awarded the Nobel Prize in Physics, and this was 2019, right? So he was in this original thing, these kind of involved in the original discovery. Didn't get it back then, but instead got it in 2019. So let's see if we can find this. Number 4. Let's see, number 3, 4. Let's see if we can find that actual statement. Do they have it in their archive? Full text. Cosmic blackbody radiation. And if we scroll down to the end, at the end, we deeply appreciate the helpfulness of Drs. Penzias and Wilson of the Bell Telephone Laboratories, Crawford Hill, New Jersey. One other possibility for closing the universe with matter providing the energy content of the universe is the assumption that the universe contains a net electron type neutrino abundance. Oh, okay. So anyways, they go into some other details about this. This is not the Penzias and Wilson one. This is the Peebles, Roll Wilkinson, Dickey, Peebles, Roll Wilkinson paper. So let us see if I can get this, if I can open up this thing. And this is probably the one that, so we can see like the reserved nature of their report once it comes up. So anyways, that was the discovery, was taking this big antenna, looking up into the sky and seeing, that is the same one that we just saw. Oh, that was the end of that previous article. Okay. So that was how this was discovered. It was predicted early on, kind of in the 60s and 70s, people made that prediction. So note added in proof, the highest frequency at which the background temperature of the sky has been measured previously was 404 megacycles per second, where a minimum temperature of minimum temperature of 16 Kelvin was observed. Combining this value with our result, we find that the average spectrum of the background radiation over this frequency range can be no steeper than lambda to the, 7th? This clearly eliminates the possibility that the radiation we observe is due to radio sources of types known to exist. Since this event, the spectrum would have to be much steeper. If I go back a page, so this is only a 2-page letter, from a combination of the above, we compute. So this is the Penzias and Wilson. This is the paper that describes the antenna and the measurements of the antenna. We compute the remaining unaccounted for antenna temperature to be 3.5 plus or minus a Kelvin. In connection with this result, it should be noted that DeGrasse et al. And Ohm give total system temperatures at these frequencies respectively. From these, it is possible to infer upper limits to the background temperature at these frequencies. These limits are, in both cases, of the same general magnitude as R value. The backlobe response. Okay, so here, the possibility of losses in the antenna horn due to imperfections in its seams was eliminated by the means of the taping test, where they, taping all the seams in the section near the throat and most of the other with aluminum tape caused no observable change in the antenna temperature. So this is all the stuff that they went through to demonstrate that it wasn't an instrumental effect, that it was actually something that was in the sky. So there we go. That is the discovery. And here it is, a measurement of the excess antenna temperature at this frequency. And it's 1, 2, 3, 4, 5, 6, 7 paragraphs. And that won the Nobel Prize. So this is one of the shortest probably Nobel Prize winning but that's ever been published. So that's Penzias and Wilson with the discovery. So now we have this cosmic microwave background. But what do you do with it? And what does the profile look like? And so there are a number of things that you would want to learn about the cosmic microwave background in order to see what mysteries of the universe could be uncovered with it. For example, is it really a blackbody spectrum? Is it really a spectrum that you'd get from a hot gas that was in thermal equilibrium with itself? So you have a hot gas, it has a well-characterized temperature, the velocity distribution of the particles in the gas are what you would expect for something that was the same, that really had a temperature, so it had the Maxwell-Boltzmann distribution of velocities and so forth. So does it produce a blackbody spectrum of that form? Then you could imagine that if there are sound waves bouncing around, which there were, sound waves bouncing around in the early universe, that you would get regions of the universe where there was compression and regions of the universe where there was rarefication or like expansion. And those would also have slightly different temperatures from the background. So the background is going to have some temperature, but then there's going to be some slightly hot regions and slightly cold regions. And so you would want to make measurements of these things to determine what kind of sound waves were there, or are there anisotropies? Maybe there's a part of the sky that has a slightly higher temperature than another part of the sky, which I guess is basically the same thing, but it could be caused by other physics besides sound waves bouncing around. Yeah, it is frustrating to try to fix something that doesn't go away. That's the nature of experimental physics, is minimizing systematic effects, thinking of ideas like what could possibly be creating this signal and eliminating all other possibilities. In fact, I just covered this in my class that I taught yesterday, is that when you are going to make a claim about some kind of discovery in physics, the real challenge is eliminating all other explanations. So oftentimes people they'll see something, they'll have a worldview, and they will see something and they will interpret what they see in terms of validating their worldview. But you're not really allowed to do that in science. Your worldview, what you think might be there, has to be your last resort. If you want science to advance, the claim that you're making in terms of discoveries that you're making has to be the last resort. You have to eliminate all other explanations, and the only thing left over is like the best explanation that's left. And so even if you want the cosmic microwave background radiation to be there, you have to eliminate all other explanations and still have the signal be there. Which is different than most people in how they interact with, stuff that happens in their day-to-day lives. Typically, people will be like, "See, this confirms my preconceived notions," instead of eliminating all possible explanations that might be even more plausible. So, and that's what they did here. Maybe this is noise caused by edge effects. Maybe it's noise caused by pigeons. Maybe it's noise caused by whatever. And then they eliminated those as possible explanations one at a time. And then you're left with, this is the cosmic microwave background radiation. So fast forward some number of years, and you arrive at a NASA mission designed to go up and look at the cosmic microwave background radiation. It is the Cosmic Background Explorer, COBE. So the COBE mission was specifically designed, here it is right here. take a look at it. So this is from the NASA website. This is what the COBE mission looked like. And it has its solar panels. It's got these cameras. They're like really low frequency microwave detecting cameras. So you have to shield it from the sun because the sun is extremely bright, kind of destroy your cameras. And the COBE mission was designed to go up and measure the temperature of the blackbody spectrum, measure the temperature of these photons coming from different parts of the sky. Now, an important thing about COBE that's different from the more recent experiments that we haven't talked about yet, but COBE was specifically designed to measure the temperature. And that is a difficult thing to do. So when we look at more recent measurements of the cosmic microwave background radiation that we'll go into more detail at another time, if we look at like the WMAP CMB map, so this is WMAP is the Wilkinson Microwave Anisotropy Probe, and it has a result that looks like this. This is what's shown when people say the cosmic microwave background radiation. This is typically the image that they bring up. There are more recent ones from the Planck spacecraft, but this is, for example, what people will show. Here's an example that shows, this is an interesting example that shows the difference between what COBE was able to measure in the early 90s, it was built in the 80s and launched and took its measurements in the 90s, and then WMAP in a decade later, and then Planck a decade after that. And you can see that, there's been a marked improvement in the angular resolution. This is mapping the whole sky. A marked improvement in the angular resolution and the sensitivity that you get, right? You can resolve smaller details. If I open this up, you can resolve smaller details with the more recent data compared to WMAP and compared to COBE. There is a significant difference, however, in the way that WMAP and Planck work and the way that COBE worked. And that WMAP and Planck, they measured differences in temperature at different parts of the sky. So they would say, I have this instrument and I'm going to point it in two slightly different directions, and I'm subtracting what I measure from the two. And so these are measuring specifically the fluctuations. So they're measuring the bright and dark spots. COBE, on the other hand, measured the temperature directly. And so it wasn't a difference measurement. It was how hot is this part of the sky? How hot is this part of the sky? Not what is the difference in temperature in this part of the sky and this part of the sky. And that is a much different animal to do. It's a lot harder when you're making measurements to measure absolute values of something. So if you have some quantity, for example, it's a lot harder. If you want to measure something like the mass of something, some substance, it's a lot easier to take a scale. So here's your scale, like this. Say you want to measure the mass of a sack of potatoes. It's easier to put a basket on here and measure a basket and then fill it up with potatoes and then measure the mass of the potatoes and then subtract the mass of the potatoes from the mass of the basket, because then you're not sensitive to the calibration. You're less sensitive to the calibration of the scale itself. So, maybe the scale, the needle in the scale, if you're looking at the scale, it's got a little dial on it. Maybe the needle gets stuck at the beginning and so it doesn't move until you get a couple pounds worth of stuff on it. So, maybe there's edge effects in terms of how does the scale operate? Does it actually measure immediately the correct mass, or do you have to get the spring compressed a little bit or the dial moving a little bit before it starts behaving the way that you want the scale to behave? So if you do like a measurement of the deflection as a function of the mass that's on top of it, you assume that it's linear, that it will deflect some angle based upon the amount of mass that's put on there. But you could imagine that before it gets started, it goes through some kind of, that someone spilled some soda pop in there, and so it's a little sticky. You may get some difference in behavior. This is what you want to have happen, but at low masses, maybe it doesn't behave that way. And so it's easier to make difference measurements. It's easier to say, well, I'll just put in something that gets me up to this threshold, and I know that the scale behaves properly from there on. And so then I make my measurement, and then I subtract these two to measure the mass of whatever it is that I'm putting in there. It's a lot harder to characterize your instrument well enough to understand its behavior all the way down until you get basically no signal. And that's what COBE did. So COBE measured the temperature in a given direction, not differences in temperature at different locations in the sky. And as a consequence, it's a subtle difference, but it's a difference that is pretty significant in terms of how you design your instrument. So COBE goes up and starts making observations or measurements of the the sky, and it returns this map. Now this map is the measurement of the temperature at different parts of the sky, and you can see that it has variations in the temperature. There are some places that are hotter than others. In this case, hot is red and cold is blue. But the where actually blue wavelengths of light is typically warmer than red wavelengths of light. Like blue wavelengths of light are higher energy than red wavelengths of light, but this is the way that we interpret it because fire is hot and ice is cold anyways. So, but this is the temperature map that they made. Now there's a lot of information that you can get out of this temperature map, but what I want to point out is that these temperature differences are tiny. Another piece, and kind of the more important piece of information that we got from COBE, so let me come back here and I'm going to open this in a new tab so that I can pull up what I think is the more impressive measurement that they made, and that is, it's not on here. So let me just pull up a new tab and see the COBE spectrum. And that is this image. Okay, so this is, so this is not quite as beautiful of an image. It's less photogenic than the other. But this is the wavelengths. So they made measurements as a function of wavelength. So at different wavelengths, they made measurements of the intensity per unit wavelength. So that's this. And so they span like an order of magnitude, basically in wavelength from half a millimeter up to 10 millimeters. So, and this is how bright the sky is at all these different wavelengths. Okay, and then they had a one parameter model. So there is a curve, so the blackbody radiation curve that was derived by Planck, Max Planck back in the day, about 120, 130 years ago, something like that. And it has a single parameter. So there's a bunch of fundamental constants to go into it, the speed of light and Boltzmann's constant, and then or Planck's constant, and then there's one parameter, and that parameter is the temperature. So you get this shape at a given temperature. If you change the temperature, you get a similar shape, but it's shifted slightly, and it extends higher in some areas and lower in other areas. Basically, you have a family of curves that come from the Planck spectrum. So if you look at the Planck spectrum at different temperatures, you get curves that look like this. So all the curves have the same shape, but as you change the temperature, you just you stretch and in certain directions and shrink it in other directions, the shape of the curve. But it's a single functional form. But you have a one parameter model. So that is the issue here. They had a single parameter, and they fit the temperature, 2.74 Kelvin, and it goes, the model is the line, goes through all of the data points. And what's interesting about this particular figure is that the actual uncertainty in the measurements, so the uncertainty in the location of these data points, is smaller than the point that's represented on the graph. Typically with the COBE data, they have to expand the data point, like the error bars on the data point, so that you can even see them, because the error bars are so small, the uncertainty in the measurement is so small that it's smaller than the point that they put on the graph to represent it. It's smaller than the dot. And that's pretty impressive. So getting this measurement is really impressive. And then you basically just fit this to, you adjust the temperature until you get a good fit. You get a measurement, you get an uncertainty to that temperature measurement, and then you do it at a different part of the sky. So COBE looks at a part of the sky, makes all these different measurements at different frequencies or different wavelengths, and then that's the data that you get for that part of the sky. You move to a different part of the sky, you do the same thing. Move to a different part of the sky, you do the same thing. You move to a different part of the sky, you do the same thing. And so now you've looked all over the sky, and you've made this measurement in all directions, and then you get this map. So this is an independent measurement of the temperature in all of these different directions, and that is impressive work. And so that's why they won the Nobel Prize. The fact that, let me move this over here. The fact that they get such a good blackbody spectrum is an indication that this was a strong indication that the Big Bang Theory, in terms of like you have a hot gas that expands, it has like a uniform temperature and then as it expands, it cools the way that you would expect a gas to cool, and then it goes through this phase transition that releases all of this radiation. The fact that the universe behaves that way, that was a strong indication that the Big Bang Theory was correct, that we understand the physics going all the way back to 400,000 years after the inception of the universe. Because if this had a different shape, if it didn't have this exact shape, then that would imply some unusual physics in the universe. It would imply, for example, maybe that all of the radiation was formed from, not from hot gas that was bouncing around, but from some kind of strange magnetic field that was causing a certain acceleration of the particles, that there would be some different physics as opposed to just basic thermodynamics. This is the kind of curve that you get from basic thermodynamics. You get different effects if you have different electromagnetic processes going on. So that's a big deal. It had a black body spectrum. That black body spectrum was 2.7 Kelvin in temperature, and the fluctuations that you got, so these fluctuations that you get, these are at a level of like 4 decimal places down. So 10 to the minus 5 Kelvin differences. So 5 decimal places down. These are fluctuations of tens of microkelvins in temperature from one place to another. And so that also is impressive. So not only, the actual precision with which they measure this has a few more decimal places that aren't recorded on this plot. So that was the COBE data. And so it made a number of important measurements. Number one is it measured the fact that the universe actually was a black body, that it had a black body spectrum. Number two is that there were temperature differences at different locations. So then what you can do is these fluctuations in temperature correspond to sound waves, wavelengths of gas pressure. Sound waves is gas pressure. So you have sound waves that are propagating through there. You get regions where gas is being compressed, and where it's compressed, the temperature goes up slightly. Where it expands, the temperature goes down slightly. And so you get hot and cold spots at different locations that correspond to these sound waves that are bouncing around in the early universe. They are frozen in place when the universe goes through the phase transition and releases all the radiation all of a sudden. Because once that happens, then the hot spots are going to release the radiation at the high temperatures, slightly higher temperatures, 5 decimal places down. And the cold regions are going to release radiation that's at slightly longer wavelengths, and that corresponds to a slightly lower temperature. So that's COBE in the 1990s. Once this was discovered, there were a number of measurements also that were taken from the ground. In fact, I believe when the COBE data were presented at a conference, this is like the worst possible speaking slot to be given, is to present research on a similar topic, or basically the same kind of measurement taken from an instrument that you designed right before the COBE data are presented. And it turned out that the group that presented before them, making similar measurements but from a ground-based observatory, they had a systematic effect in their data. And so they showed a really strange anomaly that doesn't show up in the COBE data. No, I lied. I think it was backwards. So COBE went first, and then this group followed them that had some anomaly in their data that they hadn't explained. So they present their data, and it's like, well, I guess we're wrong because the COBE data, so it was being scooped by someone who not only scooped you, but also outclassed you in terms of the quality of the data that they had. It's not like maybe the scientists were equally good, but the quality of the data that the COBE mission had compared to the quality of the data that the subsequent speaker had. So you don't want to follow the person who's going to win the Nobel Prize in your stead at a conference. But anyways, that was what happened, one of the vicissitudes of life. So this set the stage for now that we understand how the universe is put together in terms of like what the temperature is across the sky. We understand basically what's the size of the fluctuations that we want. You want to be more sensitive in 2 different ways. Number one way is you want to be more sensitive in making resolving smaller angles. So you want to be able to resolve. So here the angles that you're resolving are basically the size of these dots. Like what's the smallest dot that you see? The smallest dot is going to be something like this, which might correspond to a half a degree or a tenth of a degree or something like that in the sky. You want to be able to get higher angular resolution. So you want to be able to narrow down, like, where am I actually pointing in the sky? Have better pointing characteristics of your telescope, or better angular resolution of your detectors, so that you can make a more refined map and see maybe some small fluctuations that are inside this blob. Another thing that you want to do is be more sensitive to the temperature variations. So this might only be able to detect temperature variations in the 5th decimal place, but if you can be 10 times better, then that gets you down to the 6th decimal place, and you can see smaller fluctuations across here. So those are the two ways that you want to make improvements in this map of the cosmic microwave background in the sky, is smaller angular resolution, or better angular resolution, and better temperature sensitivity. The way that you get smaller angular resolution or better angular resolution is by designing your instrument to do that. And then the way to get better temperature sensitivity is to change from having an absolute temperature measurement to having a difference in the temperature. You're measuring the difference in temperature from one place in the sky to another, instead of trying to measure the absolute temperature everywhere. And if we look at the uncorrected CMB, you get this. So this is the COBE data uncorrected, for example. So that's what the sky actually looked like to the COBE data. And they removed what's called the dipole term. They removed the fact that there's a hot spot over here, and the big hot spot here and a big cold spot here. You make that 0. And that's how you get the average. So here's the galaxy. You can see the galaxy running through the center, this like lobe here and that point there. So that's the Milky Way galaxy. This is the average direction of the Earth going around the sun, or COBE going around the sun going around the galaxy, and the galaxy drifting through space. So that was something that I should have pointed out as well. So I guess I'll add this little clip. The actual raw COBE data look like this. The hot spot that you see here and the cold spot you see here is the Doppler effect from the motion of the Earth going around, or COBE going around the sun going through the galaxy, and the galaxy drifting in space relative to the other galaxies in the universe. So you want to remove the peculiar motion that's associated with our reference frame. And once you do that, then you get to this. Okay, so that's when you go from the cosmic microwave, the Cosmic Background Explorer, the COBE mission, and you go to the WMAP mission. So if we go to WMAP, the Wilkinson Microwave Anisotropy Probe. Now, when I first saw a talk, it was the Microwave Anisotropy Probe. Wilkinson was one of the main people on the mission, and he died right around the time that the mission launched. And so they put his name, like attached his name to it in memoriam, as a memorial to the person who kind of made the mission happen. So let's go to the WMAP mission site. Okay, and there are a couple measurements that were made from the WMAP mission. So this site has worse images. So why don't we just go directly? Why don't we just find images on the web, because those images were terrible. So we'll go to the Wikipedia article. That was a very unimpressive website. I hate to say it to people on the WMAP mission. Okay, this image, this is the cosmic microwave background radiation temperature fluctuations measured by the WMAP mission. So here you can see, if we compare it to COBE, right, here's this blob over here, this hot blob, and then you have a cold blob kind of right in the middle. Same kind of thing appears here. Here's the cold blob in the middle. Here's the hot blob on the side. But now that you have better angular resolution and better temperature sensitivity, you can see all this little hot spots and cold spots within the larger blobs. So again, if I flip back and forth between these two things, the structures that you see here are on larger scales. The structure that you see here are on a lot smaller scales. Now that's important for a number of things. As you're looking at smaller and smaller scales, like smaller and smaller angular separation, you're looking at shorter and shorter sound waves, like the wavelength of the sound that's bouncing around in the early universe. You're looking at shorter wavelengths. Okay, so what are some of the things that you can get from this information that you can't really get from COBE? Well, what you can do is you can say, all right, I'm going to say, what is the typical brightness variations, like when I look at different separations in the sky. So for example, if I look at separations from here to here, that's like something like 90 degrees apart. 90 degrees apart from there, and then another 90 degrees away, I have this kind of big hot spot here, and then here's another hot spot. So you say, if I look at things 90 degrees apart in the sky, what is the typical temperature variations that I'll see? And now what if I look at 45 degrees in the sky? So I pick an angle that's 45 degrees in the sky, and I say, how are the hot spots and the cold spots related to each other when they're separated by 45 degrees? What about 15 degrees? What about 10 degrees, 5 degrees, and so forth? And so you can narrow it down. And what that allows you to do is to determine the typical scale, like what's the most common separation between hotspots in the sky. So, here's a hotspot, and then here's a hotspot next to that. And if I come over here, there's a hotspot next to that. It's like, what's the scale of the texture that you see in the sky? That's an interesting question to ask, because that tells you basically what's the most common sound wave that the universe had at the time. And that shows up in what's called the power spectrum. So if I open up a new tab, or I just come here, and I look at the WMAP power spectrum, you get this image. These are the data. Let's look at, of course, we'll steal Wikipedia because we can. So, excuse me. So this shows WMAP is the data that are in black. So if you look at the data that are in black, you see down here, and then it rises, comes up here, and then it drops back down again. And then it comes up again, drops back down again, and then the data get like really uncertain. So the black data, here's another WMAP data point at that's way out here that has large uncertainty. So the WMAP data are good at measuring angles up to some scale, and then the instrument is no longer good, and you have to have some different instrument to make more precise measurements at smaller and smaller angular separation. So in this case, wide angular separation is on the left, and you get to, so you start at wide separation, and then you narrow it down on the sky to go to smaller and smaller and smaller angular separation. So here's 90 degrees, here's 2 degrees, 1 degree is basically where the peak is, and then half a degree down to 0.2, and so forth. This is usually shown as multipole moments. So if I lift this up, actually I'm going to shrink it a little bit so you can see the whole graph. So this, the bottom part of, wow, I have to keep going to get the whole graph. All right, the bottom part of this shows multipole moment down here. So that's basically if you say, what if I have 2 lobes? What if I have 3 lobes? What if I have 4 lobes? You spread 4 lobes equally across the sky. That's going to be the number 4. Like the multipole moment is going to be number 4. If I have 10 lobes across the sky, 10 hotspots and cold spot equally distributed across the sky, then that's these multipole moments here. A way to look at that is like stellar vibrations. So this is what I mean by the different lobes. So here's like how a star shakes, and it's got how many different wavelengths fit at a given scale. That's the multipole. So in this case, we're looking at all these different multipoles. You go to more and more, 100 lobes across the sky, 200 lobes across the sky, and that happens to be where it peaks. So that's where this shows that the most common separation between hotspots and like between 2 hotspots or between 2 cold spots, the most common separation is at 1 degree in the sky. So if we come back to the WMAP data, that says that the typical separation between these dots that you're seeing, like if you were to rub your fingers across it and say, what's the texture that I feel? That would be separations of 1 degree in the sky. A degree in the sky is about twice the separation of the full moon. So a full moon is about a half a degree in the sky. So you put 2 full moons side by side, and that's the typical separation between hotspots, like adjacent hotspots in the sky. That's what that shows. And then it also shows, what am I looking for? I'm looking for this one. It shows, okay, the power goes back down, and then another common, like the next most common separation, of course, there's all these other separations that are related to this peak, but the next peak over is at, some other separation in the sky at like, what is a half? So like 0.4 or something like that degrees in the sky. And then there's another separation over here that, that's similarly common, and then you have other peaks that go farther down. So what this is talking about, or what this is showing, is at the time of or in the early universe, you have a bunch of sound waves that are bouncing around. Let me open this up a little bit, make it a little bit bigger. So you have these sound waves. you have basically, here's the early universe, here's the very beginning of time, and then you look at like time passing in this direction, and then the universe got to some size here where you have this recombination, where the electrons combine with the protons and free up this radiation that's been trapped in the universe. So you have some sound waves that fit into here, like that one. You have another sound wave that can fit into that same box. You have this sound wave, a single wave. You have one with 2 bumps, and you have one with, so here's one with 2 bumps, there's one with 1 bump, here's one with 3 bumps. Those are the ones that kind of fit into the box. Like the sound wave propagates out, and then if that sound wave happens to have propagated over some distance in the time that the universe has had when it's opaque, before it becomes transparent, that's going to show up as a signature in the cosmic microwave background. And so these different peaks that you see correspond to those different sound waves, like the different states. This one, this might be the most common one, and then this would be the second most common one, and then this would be the third most common one, and so forth. So it's corresponding to different half wavelengths, basically, that fit in there, fit into that box. So when you have that transition time at 400,000 years, you have sound waves that are propagating through the universe that whole time, and then you select them because that's the sound waves that happen to propagate some distance in the amount of time between when the Big Bang happened and when recombination happened, when the electrons recombined, or combined for the first time. So we call it recombination, when in fact it was the first time that the electrons combined with the protons in the universe. But these different wavelengths of sound waves that were propagating in the universe is what gives you these different bumps in the power spectrum. So this is telling you basically how commonly are hotspots separated by this given separation. And then the WMAP peters out in its angular resolution at some point, and so now you get different measurements down here. And these measurements have improved as well over time. Like this is a fairly old measurement. One thing that I didn't mention is not the Planck data. If I go back to the WMAP data, this one, you'll notice that the uncertainty spreads out over here. Like there's a lot more variation down here at low multipoles than there is up at these higher multipoles. Like this uncertainty in the model. So the uncertainty in the model is the width of this shaded region. The uncertainty in the model gets smaller as you go up here. So it's like tiny up here, and then the uncertainty grows and grows and grows. So this is an important thing that I should probably clip and stick into the middle of the thing. The uncertainty in the model is tiny for small fluctuations and bigger and bigger and bigger for the large fluctuations, the ones that span the sky. The reason for that is that there's only so many 90-degree angles that you can measure in the sky. The angle is so big, you only have 4 pi steradians, you only have the sky to cover. And so there's a lot fewer measurements that you can make of oscillations or sound waves that have some number of wavelengths in the sky. So, 90-degree separation in the sky, you can only fit, 8 in one direction and 8 in another direction. So it's a lot more clunky. And so the uncertainty that you get as a consequence of the fact that you can only measure so many 90-degree angles in the sky means that you have a large variations over here compared to the precision of the instrument. So this is called cosmic variation, comes from here. And then, the universe gave us some realization of itself. The universe happened and it has these measurements. And another universe with the same broad initial conditions, like the same statistical properties of the initial conditions, would give you a slightly different set of measurements that you would make at 90 degrees. And so because you can only probe so many different 90-degree angles in the sky, you get a lot of variation that you would get from one universe to another. But when you're getting up to here where you have 500 different ways of arranging things, you can average over those 500 and the theoretical uncertainty goes down. There's a lot of, you can make a lot of 0.1 degree measurements in the sky. So, we can do 1 degree, for example. At 1 degree in the sky, there's 40,000 square degrees in the sky. So at 1 degree separation, you have 40,000 measurements that you can make. And that 40,000 measurements, in this part of the sky and this other part of the sky, that 40,000 measurements reduces the uncertainty that you get. Because now you're sampling a lot more possible measurements that you would make at 1 degree. When you go to 0.1 degree, now there's even more measurements that you can make. across the sky. And so your theoretical uncertainty gets smaller and smaller and smaller and smaller as you go to smaller and smaller separations. So here's the Planck spacecraft, the same thing. Look at that angular precision, holy smokes. So here's the cosmic variance that you get at 90 degrees and down. Here's the 1 degree angular scale. And then here's these other ones, and look at that. Wow, that's like awesome. That's amazing. So here's Planck, or here's WMAP, that petered out at about right here. So at about 0.1 degrees in the sky is where WMAP was no longer able to resolve things. And so the uncertainty in the WMAP measurement get really big after that. So that's a multipole of, 600 or so? And if we look at Planck, it's getting high precision measurements down to multipoles of like 2,000. That's huge. So it's like a factor of 5. A factor of 5 improvement in the angular precision that it can measure things. Look at that. Look at those data. That's amazing. So that's the Planck spacecraft. Boomerang was another interesting measurement that was designed to detect something different. And that is related to one of the measurements that you want to make with the cosmic microwave background radiation. Not only is like what are the wavelengths, like what's the separation there, but also what is the overall geometry. Recombobulation, yeah, exactly. So it's not quite the same as discombobulation, it's recombobulation. Like, when you're plussed. Instead of being non-plussed, you're actually plussed. Okay, so one of the things that you can do with the cosmic microwave background radiation that is unique to the cosmic microwave background radiation is you can measure, maybe it's not unique, but one of the easy measurements to make with the cosmic microwave background radiation is what is the overall geometry of the universe? How is the universe, like how do you measure things in the universe? The way that we define straight lines, for example, in the universe is light rays are straight lines. So if you have a light ray that moves like this and another light ray that moves like this, those are straight lines. And in this case, you would call it, maybe these would be parallel lines. Since the universe started at a singularity, at least that's how we understand it to have started as a singularity and everything has spread out, you would have light rays that are going to be moving apart from each other. Okay, so you have all these light rays that are moving apart from each other. If, for example, the universe had a huge amount of mass, so there's a ton of mass in the universe, and the universe actually, all that material starts getting pulled together and collapses on itself, then all these light rays that started back in the early universe would eventually turn around because the gravitational attraction of all this matter would pull it in, and eventually everything would come back together and you'd get the big crunch. So all the light is moving out in random directions, but in the future, all that light's going to come back together if the universe had a huge amount of mass in it. Turns out that it doesn't, but this was a possibility, that there's a whole lot of mass in the universe that closes the universe, pulls everything back together. Well, okay, now you have light rays that are moving out and then they're moving back in. Light rays define straight lines. And so you have a geometry that's set up in this case that looks like this. It's a closed geometry. So you have a sphere and you have light rays that are moving out. So in this is the past, and then here's the future. Light rays that are moving out from the past, and then eventually in the future are going to recombine. So maybe the present is right here. This would be the present. And time moves, in this case, in the vertical direction. Okay, so having a geometry like this means that the structures that you see in the sky, if you look in the past and you if you map out the surface of the sky, when you draw a triangle on something like this, on a surface like this, triangles don't have, the angles in the triangles don't add up to 180 degrees. If you draw a triangle on the surface like this, you get structures that look kind of like this. Okay, and the angles here add up to more than 180 degrees. Like the best example of that is to just have a gigantic triangle. If you draw a triangle on the Earth, so here's the Earth, you have this is like Quito, Ecuador. This is Nairobi, Kenya. They're both right on the equator. And then you walk due north from both of those. So you're 90 degrees away from the equator. You walk due north from both locations, and you can have whatever angle you want up here at the top. And this is a triangle that has angles that add up to more than 180 degrees. So this type of geometry, you would get, like measuring the angles in triangles tells you about the underlying geometry of the surface upon which the triangle has been drawn. So in this case, you have a closed geometry. and the angles in a triangle add up to more than 180 degrees. If, on the other hand, you have an open geometry, so you have like a saddle that looks like this, so that's kind of what your coordinate system looks like, then when you draw triangles on this, the angles add up to less than 180 degrees. You get little pointy triangles. So if you have an open structure, then the angles in the triangle add up to less than 180 degrees. If you have a closed structure, then the angles add up to more than 180 degrees. So you can do the same kind of thing here. You can look at how are the triangles in these data arranged. Like if I draw a triangle between one of the hotspots and some other hotspot and some other hotspot, given the angle that separates them. So you have two lengths and an angle, and you just say, okay, I'm going to pick a length. It might be the length corresponding to the peak in the power spectrum right here. I'm going to pick a length, and I'm going to just look at what angles exist between hotspots at a given length. That's a way of measuring triangles on the surface, like in the universe from back in the day. If I were to draw triangles on the early universe, do I get angles that add up to, do I get triangles where the angles add up to more than 180 degrees? Pen is not working. Here we go, more than 180 degrees, angles that add up to less than 180 degrees, or do I get a flat universe, kind of the way that we learn it in school, where the angles in the triangle add up to exactly 180 degrees? So these are questions that you can answer by looking at the spatial relationship between the hotspots and the cold spots in the cosmic microwave background radiation. One of the best ways to do this is to measure it at really small angular separation, and that was actually done by this Boomerang mission that was listed on here. So this Boomerang mission did that. So if we look at the Boomerang results, so you calculate it with a function called the 3-point function, Boomerang experimental results. Let's do experiment. And it's basically, you take the sides and you multiply them together in some way, and you have the angle that's in there. The details are kind of technical, and I've never actually done that particular analysis, so I'm probably not the best person to explain how that thing works. But it is basically, you draw triangles, you measure what are the lengths of the sides that you care about for this particular analysis, and then the angle between them, and you multiply them in a way, and then you just analyze what are the statistical properties of if you measure the temperature at the endpoints of this triangle. So you pick a triangle, you measure the temperature at the endpoints, and that tells you how common a triangle of that shape lands, maps onto the cosmic microwave background radiation. So the Boomerang result had a really important measurement, and they were specifically designed to make this measurement. So they knew that COBE was going up and it was going to make a lot of important measurements. And so they wanted to, what niche can we carve out that's not going to be probed by COBE or by WMAP? And this was the result that they got. Now, it doesn't look all that impressive, but what they specifically wanted to measure was this overall curvature of the universe. Is the universe flat, in that the triangles that you would draw on these different hot and cold spots, would they form a triangle that looks like this? Would they form a triangle that looks like this, or would they form a triangle that looks like this? And so the more interesting result is not the one that is shown here, but rather this one compared to the predictions that you would get. So if I look at the Boomerang result, we'll just go to the images. This right here, and this is from my alma mater as well. I can steal from my alma mater. I can steal this graph from where I went to school. So here's the actual Boomerang results. This is a subset of it, right? We saw what the footprint of the Boomerang result looked like. It was kind of a warped shape. But this is a subset of it. The point is, you look at the structure, where are these points located? Where are the hotspots and cold spots located relative to each other? And you compare that to these different curvatures. So you have a curvature here. So this is a closed universe where everything would come back together. And you would expect it to look like this. You would expect a certain sized bright spot to be more widely separated. So you get more clumpiness. If the universe was closed, there would be more clumping of these hotspots and more clumping of the cold spots, so that you would have a different structure. These ones are arranged differently than what you see here. The pattern is different. If you have an open structure, then it breaks these clumps up into smaller pieces. And so you would have a more washed out with smaller fluctuations that are spread out. Okay, so that would be an open style universe. That's one where the universe is accelerating. The expansion of the universe is accelerating not because of dark energy, but because of so the dark energy is a different beast that didn't come out until later. So that's another time. But this would be if the matter in the universe was below the critical density that it would take to cause everything to recollapse. So that would cause the universe to expand and to accelerate in its expansion, and you would get a structure in the cosmic microwave background that looks like this. Instead, what you see is a cosmic microwave background structure that looks more like the one in the middle, where you have hot spots that are, about the size of my mouse pointer, okay, and you have cold spots that are also about the size of my mouse pointer, and they're separated by, about the size of my mouse pointer. So this is the Boomerang results are most consistent with a flat universe. So this was the major discovery from Boomerang, and it also showed up in the WMAP data, so they can also make these measurements. The Boomerang result came out before the WMAP results came out, and so when they make improved measurements to the cosmic microwave background radiation by upgrading the instrument or like launching a new mission, they are specifically looking. One of the things that they're specifically looking for is what is the overall energy density of the universe? Is the universe something that's going to collapse on itself? Is it something that's expanding and spreading apart more and more rapidly in the future, not related to dark energy? Again, that's a slightly different topic. Or is it something that is the universe flat? Meaning, when you draw these triangles in the sky, the 3-point function, do you get angles that add up to 180 degrees, more than 180 degrees, or less than 180 degrees? So one of the questions is, are these fluctuations that you see in the cosmic microwave background radiation, what causes them? Why do these things happen? And the answer is these are the signature of quantum fluctuations from the very early universe. So that when the universe was really small, you have quantum fluctuations. You have particles that are bouncing around randomly. They have random initial positions because you can't localize a quantum mechanical particle all that you want, because the uncertainty principle forbids you from localizing it in phase space, localizing it in velocity or in momentum and position. There's always going to be some wiggle room. There's always going to be some randomness because of just the nature of quantum phenomena. And then those small fluctuations, you're going to have slight regions that are slightly more dense than others. So if I pull up the drawing pad, you're going to have random initial positions. If you didn't have random initial positions, you'd have some grid of particles that looks like this in all directions. And there's no reason why one region would be preferred over another region. Instead, what you get, instead of a perfectly uniform distribution, you get small fluctuations in the density. So you might get a distribution of particles that looks like this, where you have a region here that has a few more particles in it. It's like slightly overdense from its neighbors. So this is slightly overdense, these are slightly underdense. And so these seeds, these random seeds, are going to introduce those sound waves that are bouncing around. This is going to also start the collapse. You have more material in this region, it's going to have a stronger gravitational effect, and that's going to pull more stuff in. So stuff's going to come in, that's going to increase the gas pressure, that's going to send sound waves back out, and then stuff is going to come in and out, and you're going to get this an interplay between the gravitational interactions of all this stuff and the electromagnetic interactions of all this stuff, because photons and things like that, the gas pressure is going to cause bouncing, but gravity doesn't do that. Like, gravity doesn't have any repulsive force. Gravity is always attractive. And it's actually that the interplay between the interactions of these different forces that causes the difference in the heights, the relative heights of this peak to that peak to this peak to that peak, right? You have the first one is big, the second one is small, the third one is, big compared to the fourth one, this one is big compared to the next one. That's because of kind of the interplay between the compression that includes gravity and the expansion that does not include gravity. So the universe is flat as measured by the cosmic microwave background radiation. That was one of the main main discoveries, first from COBE. Boomerang was a really big improvement on the COBE results, and then WMAP came along and made the next refinement on that. So these are all kinds of information that you can get from the cosmic microwave background radiation that started from this radio telescope in New Jersey where they couldn't get rid of the noise that they saw in their detector. So that is the cosmic microwave background up to this point. I mean, we have new measurements. We have new measurements from the Fermi telescope, not Fermi, from Planck. Now, the Planck mission was not a NASA mission. Planck was an ESA mission. So the European Space Agency did the Planck mission. But it has this, made the same map, but it's a refinement on the map. So there we go. That is the cosmic microwave background radiation in a nutshell. There are more details that I can talk about, as we expand into like what else can we learn from the cosmic microwave background radiation. So what I wanted to go over today was just how did we make these measurements? What were some of the groundbreaking measurements that came from it, and some of the early missions that were, well, COBE in particular, the early mission that went into it. In the future, we'll talk about what does this imply for the overall composition of the universe and the structure and things like that. But that will take that'll be on another day. So there we go.